Hello, everyone. Good morning, good afternoon. A very warm welcome. I'm delighted to welcome our speaker, Professor Linfei Li. He's an assistant professor at Civil and Environmental Engineering at Florida International University, so our very friendly neighbors. He'll be talking about nanomaterials in concrete, engineering the future of infrastructure. Professor Li is an assistant professor in the Department of Civil and Environmental Engineering at FIU, as I just mentioned. Before that, he earned his PhD in civil from University of Colorado Boulder, and subsequently he worked as a postdoc before serving as director of R&D at Prometheus Materials. Prior to joining FIU, he was a research assistant professor at the University of Maine. As PI or co-PI, he secured significant research funding from US DOE, USDA, DOT, and other agencies. His research focuses on nanoengineered concrete, multi-physics coupling, well cementing, geopolymer systems, FRC, and recycled concrete materials. He's an active member of EMI and numerous ACI technical committees. So thank you very much, Dr. Li, for doing this. We appreciate it very much, and the floor is all yours.
All right. Thank you, Brinoy, for your kind introduction and host me at the University of Miami. So as you can see, the topic Brinoy already introduced a little bit is about the nanomaterials in concrete. So today we're going to talk about how we can use the nanomaterials in concrete and how we can engineer that. Oops. All right. So talking about nano stuff in concrete, like back to over 20 years ago. So it was first initiated by Dr. Shah. So I guess most of the audience know him. So he hosted a symposium in 2003. At that time, people started talking about, okay, maybe we can consider using nanotechnology in concrete. So I took this image from Dr. Konstantin Sobolov's publication back to exactly 20 years ago. As you can see, when we started talking about the concrete, conventional concrete, that was like basically cement, aggregates, and coarse aggregate, right? So, and later on we shift to we always want to make our concrete stronger and also durable. So that's why the high strength, high performance concrete came in. So we started adding metakaolin, silica film, or the fine supplementary cement materials in it. And after that, we keep going, dive into deeper, and then we think, oh, maybe we can do some nanomaterials in that as well. So there are a couple of different types of nanomaterials in, right? So so we started from like when people claim that there's a 1D, 2D, and 3D nanomaterials. So give you some examples, like the 1D nanomaterial, like nanosilica, they're kind of a spherical particle shape. Or 2D materials, we took this TEM image from Emory. So it's a cellulose nanofibril. And also, there are some 3D microstructures of the nanomaterials, like in carbon nanotubes. But why nanomaterials in concrete? So first of all, we have to know, right? Everybody knows that concrete is a porous material, right? So if we took a look at the microstructures, all the buildings we use a lot in concrete, so we see it's a pretty solid block, right? But if you dive in, focus on by using like some microscope, you see the mesostructure. You have cement, you have sand particles, you have aggregates, you still form like a pretty solid microstructure. But you further dive in the microstructure level, cement paste. You have unhydrated cement, you have hydrated cement. You will be able to see some pores on it, but still not much. But if you further dive in to the nanostructure, so you can see all the CSH, all the crystals growing, all the itrangite, you can see there are tons of porous media, you can play with it. So that's how we start thinking about maybe we can use the nanomaterials in it, right? But give you some background, the porosity of concrete is usually about 12 to 18%, but the porosity of cement is 40%. So the rocks, the gravels, the sand, maybe you cannot do much things with nanomaterial, but cement, you have a huge possibility to play with nanomaterials in it. So several things we've been investigating in the past years, and also other fantastic researchers. So we know the nanomaterials could do a lot of good jobs in concrete. Basically, it's right now it's in the lab scale. So we have demonstrated different types of nanomaterials can improve the mechanical performance because itself has a superior mechanical performance. And it can also dense the microstructure. So apparently durability is a big issue for the concrete. So if you can have a denser microstructure, so which means by filling with nanomaterials, that means your concrete is denser as well, and then improve the durability. a lot of research also talking about improved hydration. So there is a classical theory called nucleation sealing effect. So because nanomaterials is very small, so when you add that at the beginning during the hydration process, that the nanomaterials can serve as a seed. So basically, all the CSH acids can grow in on the surface of that. So you can improve the hydration as well. Self-healing, that's another hot topic recently. People talk a lot. But as a nanomaterial itself, some of them, for example, nanosilica, nanolumina, they can serve as they can form the pozzolanic reaction to improve the hydration as well. But basically, once you have the cracks opening, you have the nanosilica in it. So that's why the nanosilica can further react with some of the unhydrated cement particles. So basically, you have self-healing properties to heal the cracks. And self-sensing is not new, but recently in the past several years, MIT developed something called electroconductive concrete or energy storage concrete. So basically, people started incorporate some carbon black or carbon-based nanomaterials. They can make their concrete not only self-sensing, but at the same time, they can store the energy in that. So this basically, we got this data from Web of Science. So you can see there are still getting a lot of interest, tons of publications in the past years. So it's still in the growing trend. So now we know all the background of nanomaterials. We know this is a fantastic material. They have tons of different advantages on it, but we should adopt that in the real world application, right? But the problem is like, the reality is, well, if you search online, you can see only in the United States, we only have I would say less than 5 demonstration projects. So I took 2 of them. One is from Indiana DOT, so people incorporated nanosilica to do a bridge deck pouring, and the other one from Corvallis, Oregon. So people are using cellulose nanocrystals, doing some parking lot, and also the box girder demonstration projects. So you cannot find like even 10 projects happening in the US, but we already know this material is good. Why is that? Simply say there are only 2 things. One is about the dispersion of the nanomaterials, because that's the nanomaterials, when you really dive the materials into the nano levels, you have the van der Waals forces problem. So the nanomaterial is very, very easy to agglomerate together. So you will not show the magic from nano. So basically you have agglomerated like micro level particles. So it does not work very well, but it's kind of like correlated is at the cost, because we all know, I mean, doing revolution on the concrete is very challenging. It's not because of we cannot create a better concrete, it's all because of the cost, because concrete is so cheap. Now the question is how you can basically incorporate like a relatively expensive material into a relatively cheap material and for a wide application. So I mean, in the past years, I kept asking myself, where is the future of nanomaterials? So a couple of things we figured out in the past years is that we kind of like shift to 2 different directions. One thing is like we're thinking about if we can have nanomaterials cheaper and sustainable, so we can get something extra credits from that, right? And also you can kind of be more cost compatible to the concrete. And the other thing is like for some of the applications infrastructure, if you do not care too much about the cost, for example, some high-end applications, some special application may be possible. So here we're going 2 different projects for today. So the first project I finished a couple of years ago when I was a PhD student. So basically we're incorporating nanomaterials for repair the CO2 storage leakage. The other one is an ongoing project. So currently doing is basically we're using cellulose nanofibril. So we're using that as an internal curing agent. So let's dive into the first project. So I mean, back to 10 years ago, it was a quite hot topic. People talk about geological storage capacity of CO2, and people figured out there is a huge potential. You can just storage the CO2 underground, because at this moment, we do not exactly know how to use the CO2 as energy. So temporarily store them underground will be a possible way to do it. So at the same time, you can have the oil produced. So basically, it's more like a pipeline system. So DOE started like inject or basically capture all the CO2 from the atmosphere, and then they use the system, so the wearable system to inject the CO2 underground. But if you take a look at this this wellbore system, so basically it has a steel casing in the middle, so it's pretty narrow. It's about like the width of that sometimes can go below 3 inches. And then you have the rock formation. So basically people start and drill a hole on it and then put the steel in it. But at the same time, you also have to fill the cement in the middle, trying to fill the gaps. Otherwise, you know, the gas or the oils is going to be leak, right? But the problem is like for this kind of cement, it has to inject from the steel pipe and then go all the way to the bottom and flowing back to fill all the gaps. So which means this kind of cement materials, they are very, very flowable, and they do not have any sand particles or aggregates in that. So as a result, you can imagine in the underground environment, this kind of cement, because it's very thin, and also the underground harsh environment, high temperature, high pressure, so the cement is very, very easy to get cracked. So once the cement get cracked, well, the steel casing is only 3 inches diameter. How you can send the people like 1 mile or 2 miles underneath to fix it? So that's why we developed this kind of technology. It's called nanoparticle injection technology. So simply say the idea is like all the nanoparticles, they have the I would not say not all of them, but most of them, they have the surface charge on it. So we kind of like borrow this idea because of the surface charge. So we can kind of like use basically generate like electron migration system. So some of you may be very familiar with this testing setup. It's basically the SGM standard rapid chlorine penetration testing system, but we further did some modification on it. So one side, we did not use the sodium chloride solution, but instead we use a nanoparticle solution in that. So because of the surface charge of that, so you can generate like electron migration, you can further use the electrical driven force and push the nanomaterials into your cement, which can help to seal, basically to dense the microstructure, but more important, to seal the cracks. So this is basically the idea. So exactly the same setup on the RCPT test. So about this nanoparticle injection, or we call nano repair. So we started doing experiment. So we use something called type G well cement. So it's not, I don't think it's ASTM standardized, but it was listed in the API, American Petroleum Institute standard. So in the standard, they require you to use water cement ratio as 0.44. Imagine if you have water cement ratio as 0.44 without any aggregates. So it's being just like a liquid. It's very, very flowable. So this is how they use for the underground project. And we started with an intact sample. So see how it works with injection. But at the same time, we also want to see if we really have the cracks on that. So we generate some, artificially generate some cracks as age samples. And then we put the samples as fully saturated, and then we start running the test. So we do not know exactly which nanoparticle will be the best. So we list a couple of them as a candidates. So including a colloidal nanosilica with a 22 nanometers diameter nanoalumina. So the TEOS is another, what we call like a precursor of a colloidal nanosilica. So it has better agglomeration control because it does not form the particles immediately. But at the same time, it's a trade-off. It has weaker surface charge. And the other one is the organic nano particle. So it's called nanogel. So it's basically use polyacrylamide cross-linked with base acrylamide. So we have 4 different types of them. So we just play with them and see which one showing us the best performance. So we started from the lab scale testing. So the voltage is about 20 volts, just keep in SIP. And injection time is exactly as the RCPT test. We use 12 hours. And temperature is just controlled as room temperature, and there's no extra pressure happen on it. So some of the results we have. So first of all, we measure the porosity of the cement. So as you can imagine, there's no accuracy in that, as also shown in the previous slides. So the cement itself has around like 40% of the porosity. So we measure exactly the same. We got like 42.13%. So, and then we set up the sample to run in the test. And then after 12 hours, we get it out. So we're trying to measure it's pretty tricky of measure how the nanoparticles seal the cracks. So we started from the porosity measurement. So basically we have the sample, we cut it every 10 millimeters as a slice, and then we'll measure the average porosity of that. As you can see, we have a pretty clear trend. So if you close to injection head, there were like about, I would like see more than 2% of the porosity decrease. But if we do the percentage of that, so as you can see for intact sample, so the colloidal nanosilica show the best performance. And for the age samples, it's different. So here may need a little bit more information about the nanogel, because nanogel is a very unique material. So when you add that basic cross-link at the beginning, so the nanogel is a nanoparticle, but going through the time, so this material is going to expand. So which means if you have an intact sample, so this nanogel, once you inject them in, it's going to expand and then further damage your cement. It's kind of tricky. But for age samples, since you already have large cracks, the cracks in that, so this kind of expansion actually will help to seal the cracks. We also did another BET test on it using nitrogen gas driven. So because again, like we will not be able to directly measure the failing. So we're just the different types of indirect testing trying to prove the concept. So we're measuring the surface area of the pores. As you can see, for untreated samples, just oil well cement samples, it has a relatively large surface area of the pores. But since you have the nanoparticle injected, all the pores are filled by the nanomaterials. So basically, you have a relatively lower surface area of the pores. We also did some X-ray macroscopy. So for this one, so we custom some small samples, and then basically we have a cup and as a kind of holder, and then we just add a little bit of water at the bottom. So basically we're trying to see, okay, once we have the nanoparticle injected, I imagine our sample is going to be more it's going to be denser. So we're expecting the water uptaking will be much lower. So that's why we set this X-ray macroscopy to see how it works, how the water move up to the top of the sample. And some of the results we're getting. So from left-hand side, it's basically like just untreated sample. On the right-hand side, it's an injected sample. As you can see, there is a clear trend about the intensity, which has been significantly dropped. And also based on the derivation of that, we'll be able to target the wetting front as well. So basically, from the X-ray macroscopy, we'll be able to see the nano. It's kind of like indirectly proved concept. The nanoparticles is also successful being injected, as well as can make the macrostructure denser. Oh, one more thing, for the early age profile and later age profile, for early age, we started measuring, doing the scanning immediately, but later age is basically, every time you have to run the test, it took like 3 hours. So basically we just run 2 tests. A little bit more information about the SEM, also took a look. So on the left-hand side, if you don't have any injection untreated, you will be able to easily capture, observe a lot of pores on it. But on the right-hand side, I mean, you still have some pores, but we'll be able to find some of the pores has been sealed by the injected nanoparticles, so which is very encouraging. Again, like we also did some chloride permeability testing. So, because imagine if you have a lot of pores, your sample is fully saturated. So that means you have relatively higher electroconductivity. But since silica is more like what we call like semi-insulation material. So basically, if you have your nanosilica sealed in the pores, so the charges or electrons will not be able to pass by. So that's why we did the test, and then on one untreated sample, no injected sample, the other one with injection. Because as you can see, there is a clear trend as well. So the charge passed, basically, or the current passed, is much significantly lower, about 24% decrease, which means the chlorine ions, once you apply the external current, is not easy to transport from one side to the other side of the sample, just because of the injection of nanoparticles. All right, so we proved the concept from the small scale. Then we think about maybe we can scale that up. So we did a prototype test. I have to say this work took us a lot of effort trying to design and going back and forth with the manufacturer. So we finally built this pressure vessel. So trying to mimic the real underground environment. So this pressure vessel, as you can see from the drawing, is about almost 10 feet high. So all the bolts, every time when we open that, we have to use the hydraulic wrench. Even open the lid is going to take us like a whole day to do that. And then for mimic the rock formation, so we cut some hollow concrete piles on it. So this kind of things, because at that time we double check the strings, the elastic modulus of the rock surrounding and concrete, they're pretty similar. So that's what we can use. We use that to mimic the rock formation. But regarding the capacity of this pressure vessel, so we'll be able to do a full-scale underground environment simulation. But at the same time, this kind of can pressure up to 14.2 megapascal. So imagine if this fully pressured, it's going to be like a small-scale nuclear bomb. And it can also hold the temperature up to 90 degrees. So we're using a 90 degree C. So we're using that to mimic the cement curing in a realistic station. So for the test setup, so we set up a steel casing, which is exactly the same size for the underground project. So we put that in the middle, and then we cast the cement in the middle between the concrete surrounding as well as the steel casing. And then later on, we took it out, and then we run the injection. So we set up like two reservoirs, one side as we did for the small scale, one side is the sodium hydroxide, the other one is the nanosilica. Because we figured out nanosilica might be the one of the most promising ones. So that's why we took nanosilica as one, but we also test other different types of that. So to mimic the real underground environment, so we boost up the temperature from room temperature as we did for the lab scale to 80 degrees C. And also we pressurize that from atmospheric pressure to 6.89 megapascal. We didn't go to the maximum because I feel like we have some safety concerns on that. But also because the sample is much, much larger. So that's why the injection time extended from 12 hours to 100 hours, and also the voltage 12 volts to 60 volts. So some preliminary data we got from that. So as you can see, we did same thing. So we basically drew a core from the sample. So and then we cut that into slices. We just measure the porosity of that. We got a pretty similar trend, but I think they're relatively consistent from different types of the nanomaterials. So for example, like we have porosity for 2.13%, and then with alumina colloidal nanosilica nanogel, we'll be able to see some porosity decrease. And then of course we calculate the relative porosity change. So we didn't do much sense on that until the project ends, but since we measured the porosity, I think it's kind of like partially success of this project. So after we done the work, experiment work, we're thinking about like, oh, maybe we can do a little bit modeling, can save us a lot of time trying to figure out how we can optimize the nanoparticle injection. So that's why we started brainstorming how we can model in the nanoparticle injection process. At the same time, we also thought there might be a possibility because you are setting exactly the same setup for rapid chloride penetration as well as chloride removal. So maybe once we inject the nanoparticles at the same time, we can also push the existed chloride ions outside from the system. So we can have kind of like a dual benefits on it. So for modeling this process, I guess most of them we know chloride diffusion from, we can use that easy to use a Fick's law, right? But since in this case, you have the external current applied, so it's not only about the diffusion problem, so you also have the external current applied. So that's why we have to further extend the Fick's law to the Nernst-Planck equation. So you have two parts. You have the diffusion part. You also have the electro-driven, or we call migration part on that. So, but the problem is like in this case, you have two different variables. One is the concentration, the other one is the current. So that's why you can't solve two variables in one equation. So which means we have to use another equation. So we're basically coupling that with a Paulsen's equation. So now we'll be able to solve two different variables by using two different equations. So we develop finite element modeling and then just solve the problems like the coupling equation together. So here, just give you some examples of some of the parameters we're using. So we consider in the system, from the injection head, we have the silica ions, nanosilica, and on the other side, we're using sodium hydroxide. So we have sodium hydroxide on the other side of the reservoir. But we also consider in the system, so we have some of the ions already exist in the system. So you have chloride ions, you have potassium ions in it, and also we'll be able to dig out all the diffusivity of each ions, the binding capacity, as well as the surface charge as valence. So finally, so about the inertial condition and boundary condition, which we just introduced, and for the voltage, so because we set up the external current, so the positive side will be sodium hydroxide, and the negative side will be the nanosilica. Some of the results we're having here. So as you can see, the first figure on the left-hand side showing how the nanosilica silicon ions penetrate or concentrate into or basically be pushed into the into the cement samples. So from 3 hours, 6 hours, 12 hours, we'll be able to see some of the excuse me, some of the injection, and at the same time we'll be able to see like the sodium ions change, as well as the hydroxide ions change, as well as potassium ions change because of the electron current applied in the system. So some of the negative ions will push to the positive side, and positive ions will push to the negative side. And the last one is about chloride removal. As we mentioned earlier, so the chloride ions, we saw that might be a possibility. You have the dual benefits because chloride ions also have the surface charge. So if you set up this system, so the chloride ions will be possibly removed from the cement samples. So we did modeling as well as some experiments. So basically for the experiment, we first of all, we run the RCPG. So we intentionally inject the chloride ions into the cement sample. So we have initial kind of like content or concentration of the chloride ion in the system. And after that, so we run another round, exactly same test up, but just replace the sodium chloride solution with a nanosilica solution. So we run another round of tests. As you can see, there are some of the decrease of the chloride ions. From the far end, there is not much difference, but from the end close to the injection, a lot of chloride ions is being pushed to the other side. And again, like we do the modeling on that, and then we got pretty good agreement on it as well. All right, I might talk too fast, but we can certainly take a break on that. So just a little bit of conclusion on it from this project. So we know the nanomaterials, apparently they're costly, but ideally you can justify that for some special infrastructure applications, for example, underground project, because it's very difficult to send the people like 1 mile or 2 miles underground to fix the cracks. And the other thing, which is also very important, is that you do not exactly know where the cracks is. So that's why using this technology is showing like a great potential. So you can basically remotely seal the cracks and then repair all the potential leakages. So again, this technology could be applied for some CO2 underground storage project, which and also as well as geothermal wells or even nuclear power plants. And through this, the development of this technology, so we can remotely reduce the process, repair cracks, while also benefit from the chloride removal. So again, here I want to make a conclusion on that. I think this technology will not be applicable for regular infrastructure because I think the cost of this technology is not worth the effort. But for some specialized infrastructure, that might be considered. And finally, so with the wet model, so we use the Nernst-Planck equation coupled with Paulsen's equation. So we'll be able to modeling this kind of electron migration process about the nanoparticle injection. But again, if you want to do that, so this coupling model can also be applied to any different types of chloride chloride penetration problem, because in the past we just used Fick's law, but we never considered all the ionic strengths in the system, like potassium ions, sodium ions in your pore solution. So I think if we want to have a relatively accurate prediction, I think using this model will be much better than the current Fick's law. Now we can move to project 2. So project 2 is I'm very excited about this project because we're getting a lot of attention. So because internal curing in the past in the past year is a big deal, even like FHWA. So they form committee. It's called, I think, EPIC squared. So people are pushing forward about internal curing technology of the concrete. So this is an ongoing project. So we don't have all the results concluded, but we can talk about internal curing. So why we have to do internal curing? So as everyone know, like concrete, you need to be cured. You need to keep getting the moisture from the atmosphere, right? So that's why for the on-site applications, you have to either keep pouring the water or doing the fog on it, or you just cover by the burlap to keep the moisture. So your cement will have enough water or moisture to keep hydrating, right? But the internal curing technology is basically you kind of incorporate kind of the material which can hold some of the water. It's kind of like a micro reservoir. This water can slowly release during the hydration process of the cement. So that means you do not have to keep adding the fogs or the water or cover that. So basically the concrete can be cured very well. But at the same time, so give you a quick fun image. It's like if you have a baby, right? So if you keep giving concrete or cement is your baby, right? So if you keep giving cement the milk, which means the water, so cement will be happy. Cement will grow stronger and have pretty good microstructure as well as the strength, performance, durability, anything. But if you do not have enough water in your system, and your baby will start crying, right? Because I need the water, I need the milk, right? So this is how the internal curing could possibly continuously giving the cement the water and moisture, so the cement can be cured very well, so they can grow up. If you don't have enough moisture or water in your system, as a result, you have the shrinkage of concrete. So shrinkage of concrete, as everyone knows, is a big problem, especially for some of the types of the shrinkage, like plastic shrinkage or autogenous shrinkage. They happen in the very early stage. So we know for a lot of types of concrete materials, the concrete is pretty dense. So it has a pretty good durability. But imagine if your concrete start cracking in the first months or just first 10 days, and you'll be in trouble because all the harmful ions like chloride or de-icing salts, everything will be easily penetrating into the system. You will get the corrosion of rebar. If you use for coastal infrastructure, the sulfate ions will be easy to penetrate as well. So we have a lot of problems. So shrinkage is a really big deal for the concrete durability. And this just give you a little bit concept of one thing we're talking about, because we're talking about internal curing. So internal curing is directly benefits the autogenous shrinkage, so which happens in the first 10 days of the concrete. So autogenous shrinkage is basically because for the cement, so they need the water to be cured, right? But right now, since we're driving crazily, of using high strength or high strength concrete or UHPC. So we use a lot of like low water to cement ratio concrete. So in low water to cement ratio concrete, which means you do not have enough water in your system to continuously feed your cement. So as a result, the cement will continuously pour the water from the pores, and then they will generate like kind of like a negative pressure. So we call that self-desiccation process. So that's why this kind of like pressure will finally cause a shrinkage and crack your cement. So a little bit more information. So the self-desiccation will start immediately from the relative humidity drop. But consider your cement is hydrating, so the cement is gaining strength over and over. So people did not think at the beginning that would be a problem. But autogenous shrinkage, people define as if you have a relative humidity below 93%, you definitely need to consider the risk of the autogenous shrinkage, which will happen to your concrete and generate the cracks on it. And it is more, as I mentioned, it's specific for the low water cement ratio. If your system, the water cement ratio is below 0.4, so you have a more serious problem because you don't have enough water in your system. A little bit information, some of the available technology. I think the first one is light weight aggregates. So light weight aggregates has been propped very well in the past years because this material is relatively cheap, and then you can just use that to replace some of the fine aggregates. It has, as you can see from the photo, yeah, it's relatively porous, so it can hold a lot of water. So what you need to do is just pre-soak the lightweight aggregates. So it has relatively high absorption capacity. So the lightweight aggregate can carry some of the water in the system and later on just release that. But the problem is that, from the compounding mechanics point of view, so because your aggregates becomes more porous, so that's why we'll also reduce the strength of concrete. So we have a paper published last year. So we did some work with the lightweight aggregate, but the same thing, the more we are adding, so we're saying the strength was going down. And the other one has been mentioned many times is SAP, super absorbent polymer. So if you don't know this types of polymer, so it's being widely used for the baby diaper. So, but this kind of polymer is that it can also absorb a lot of water to basically expanding. So the good thing for this kind of polymer is that you only need to add less than 1% as additive. You don't have to replace anything from your concrete matrix. And they can serve as a macro reservoir. So again, this material can hold the water into the system and release the water. But recently, adding SAP into the concrete system just draw like a significant durability concern because this material, is going to be biodegradable. And after several years it's down, so this material is going to leave a pretty big pores in in your concrete matrix, which will draw a significant concern, for example, the freeze-thaw damage. Because for freeze-thaw, you have to control well of the size of the pores, otherwise you'll be in problem. So how can nanomaterials help? So here we want to introduce one types of nanomaterials we'll be using specific for the internal curing. It's called cellulose nanofibril. So people also call that CNFs as well. So as you can see, we took this image. We got cellulose nanofibril from University of Maine. PDC is a process development center. So this is 3% CNF slurry with 97% of water. And it's more like a gel, or a cream. So you can imagine how this material can hold water. So if you took some image from the TEM, you'll be able to see this is a fiber. This is not a cream. And why we're using that? So first of all, we know this material is a wood-based product, so it's sustainable, it's regenerative, and the process of getting that is pretty simple. You don't have to do any chemical modification. You just need to do the mechanical grinding. And the University of Maine, they have an industry-sized facility. So they're basically generating the cellulose nanofibril and ship internationally. So we know this material has a length around 225 micrometer, but the diameter is from 5 to 200 nanometers in range. So that's why we can call that nanomaterials. And the other thing which just give you data is like, based on what we found so far, so 1 gram of cellulose nanofibril can hold more than 23 grams of water. So that's impressive. So this is why we started thinking about, yeah, we can use that for internal curing purposes maybe. But more importantly, compared to the other two, is that we're not only focused on mitigate the autogenous shrinkage and internal curing agent, but because this material is a nanomaterials, so we also want to see if there is a possibility we can serve as a nanomaterial in your system and also basically strengthen your concrete, like make it more like a denser or like just improve the durability as well. So we can basically do two things at the same time. But for internal curing purposes, I think the first challenge we're having is how we can determine the water retention value of that, or because the CEF, well, it do not carry. We cannot ask them to carry excessive free water into system. Otherwise, if you have excessive water in your system, so basically you release immediately, you bring up the water to cement ratio, so which is not good, right? Because we always want to keep the water cement ratio. So this is why we have to determine what is the SSD, the saturated surface right condition of the CF. But it is really challenging. It's not like for the lightweight aggregates, you can do ASTM standardized testing. For the superabsorbent polymer, you can also do the T-back master. But for this material, there's no exact way how we can quantify that as acetate conditions. So here, my student and I, we spent a lot of effort on that, trying to figure it out. So we did. It turns out we used two different methods to do that. The first one, we use a centrifuge. So for centrifuge, there are also two different standards which have been published. People claim that as SSD for cellulose nanofibril. So one's TAPI, so they use 900 G as gravity for 30 minutes. The other one is the international standard, uses 3000 G for 30 minutes. So we run both of them, and then we've been saying like, okay, so for 900 G, so what the retention value for the CF is about like a little bit over 28 grams per gram. And for the 3000 G, so it's basically going to below 20, a little slightly below 23 grams per gram. So we're not, so all different standards which are good give us a reference, but we do not know which one is correct, how we can quantify the acetate condition. So then we incorporate the second method trying to figure it out. So it's very simple. It's just a flow table test, because we know when we're adding the nanomaterials into the cement system. So the nanomaterials basically, because of high surface area, will reduce the flowability of the cement paste. But at the same time, we're trying to see, okay, because we have the cellulose nanofiber in the system carrying the water, so we want to make sure we have the water we're carrying is not going to be contribute to the water cement ratio. So that's why we developed this kind of equation and trying to separate the water use for increase the water cement ratio and the water use for internal curing purposes. So what we got here is that first of all, we just do a calibration by using the flow table test just for the cement with different water to cement ratio, and we incorporate the CNF. We quantify that as a dry CNF content with two different water cement ratio. We did the fitting on it. And then finally, we'll be able, based on the equation we derived, so we'll be able to quantify that, okay, the water retention value is kind of around like 23 grams. So from this range, we can see, okay, 23 grams is good at this moment. So then following is the desorption kinetics. So because we also want to know, we know how much water the CNFs can hold, but we also want to know how the CNFs release water at different relative humidity. So we use a celery source solution to create different relative humidity. So you can see the desorption rate here from different relative humidity. And on the right-hand side is the desorption isotherm. So we're kind of like comparing the cellulose nanofiber we're using with the traditional lightweight aggregates as well as the traditional SAP. As you can see, the good thing is like for cellulose nanofiber, this material can release more water in terms of degree of saturation compared to the lightweight aggregate as well as SP as a high relative humidity. I think this created like a huge potential, like even your system start hydrating, your relative humidity is going down, but even it's still in a high level, like let's see 97% or 95%. So the CNFs is very sensitive. They will start releasing water from the system. But lightweight aggregates or SAP, they may not respond immediately or just basically have a slower response. And we started incorporating that in the cement. So we just did one water cement ratio, one mix design at this moment. So we water cement ratio 0.35, but we try to use three different dosages of CNF from 0.1% cement weight percentage to 0.3 cement weight percentage, because for nanomaterials, apparently you don't want to add too much. So the first picture show like this about 3% of the cellulose nanofiber we're getting originally. So first of all, we use a high-speed shear mixer. So we pre-mix that, doing like a pre-dispersion to create like a diluted celery. So basically, we use the water, including the water cement ratio with 3% cellulose nanofibril. So we create like a celery, and then we use the celery to further mix it with the cement for another 4 minutes. And we start measuring, so we got a lot of interesting findings from, some of them may be different from what other people find as well. So for final setting time and hydrogen kinetics, For final setting time, we just use the weekend needle. Surprisingly, a lot of people talking about the nucleation effect, but our final setting time is keep getting delayed with more and more cellulose nanofiber added into the system. And we did some hydrogen kinetics as well, so it's still ongoing. So we only have result from 0.1 and 0.2%. As you can see, there's not much difference, but you can see there is a slight delay from adding the cellulose nanofibril. I think it's kind of like debate on that. So a lot of people talking about either you have the nucleation effect, you can accelerate the hydration process, but on the other side, so the nanoparticle is going to stick on the surface of the cement particle. So it's kind of like being like a block or a barrier to stop the water directly contact with the cement. So that's another theory. People are saying we're not very clear if the nanomaterials adding will accelerate the hydration or delay the hydration. But at this moment, based on what we found, without any ultrasonic dispersion, we saw there is a delay in the hydration process. But surprisingly, on the other side, if you see the cumulative heat, actually in the later stage, it goes up. It's higher than the reference sample. And we also did the autogenous shrinkage test. This is the most important thing because they can quantify how our cellulose nanofibril surface agents can mitigate the shrinkage. So we got some pretty good results. As you can see from reference sample, they had the largest shrinkage for up to 10 days is about like 500 micron strain. And with continuous adding more and more CNF into the system, we'll be able to lower the autogenous shrinkage. We all see from all the samples, we see there is an initial expansion. And so we talk a lot about that. We thought that might be because of the bleeding issue of the cement at the beginning. And if you just cut off the initial expansions, it'll be more clear to see what will be the difference between without adding the CNFs or adding different dosages of CNFs. We also did some mechanical testing tests because remember, we're trying to use the nanomaterials not only as internal curing agent, but we also want to see if that can improve the mechanical performance of that. So now we only be able to show some result from 7 days, but it's kind of tricky because when we add 0.1% of CNF, we'll be able to see a slightly increase in the compressive strength. But if we add more 0.2 or 0.3%, we see like over 10% of drop of the compressive strength. But it could be, it could be one reason we did not do any specific pre-dispersion process because we just use a high shear force mixer. So we hope we can see more promising result or good result to kind of like reflect the curve. Maybe we can add more because for internal curing purposes, I think 0.1% might not be enough for completely remove the shrinkage, but we'll be able to see some decrease as well. And finally, that's another direct observation. So for getting the relative humidity, because like the relative humidity in your system is basically the trigger to generate the autogenous shrinkage. So we're at the beginning, we also have a hard time because the relative humidity for the cement solution is very high. So relatively most of the sensors cannot work because because the hydrogen of heat will generate a lot of vapors. So that will kind of like damage or make your sensors not very accurate. So finally, we turned out of using the setup. So basically, we collect we crush the powders, we put that into the tube, and then we set up like the sensor in that, and then just basically measure the relative humidity in the powders. We started from after the final setting time, and on the right hand side, you can see apparently adding the even 0.1% of CNFs can keep the relative humidity for about like I would say like about like 94%, so up to 7 days in the isolated system, which is apparently much better than the reference samples. All right, finally conclusion. So CNFs, what we have show a significant potential for mitigating the autogenous shrinkage, while simultaneously improving the mechanical performance of concrete, but you can depends on how much what kind of dosage you are adding into the system. But we're thinking about maybe dispersion will help. And the CNFs we use now is a bleach CNF. So, and also finely processed. So that's why you see the 90 numbers on that. It's basically the human call that 90% fine. So we're thinking about maybe we do not have to grind it to that fine, but at the same time, we don't have to bleach it. So that's why maybe we can use lignocellulose or like coarser cellulose nanofibrils, so provided by human. So we'll further investigate them to see how that will affect the performance, because apparently if you don't have to bleach that and then you can use a less fine CNF, the cost will bring down as well. Yeah, the dispersion effect, as I just mentioned, we haven't started yet because I just got the equipment ready. But the dispersion effect, I think we'll be able to help to disperse the cellulose nanofibril better, at least better, in the cement or concrete system. So in that case, I hope we'll be able to see if even we add 0.2 or 0.3% at the cement weight, we'll still be able to see the increase of the mechanical performance. And the other thing is, like, even we did some indirect measurement, like we use a centrifuge testing, we use a flow table testing combined, we can kind of temporarily made a conclusion. We said 23 grams per gram is the water retention value for the CNF, but it's all like indirect measurement. So we really want to see if we will be able to capture the water movement from the CNF to the cement during the hydration process. So this will give us like a direct observation. So we can make sure and tweak our CNF to make sure there is no excessive water to basically increase the water to cement ratio, but we have perfectly amount of water in the CNF can later on reduce released to the system for the internal curing purposes. So in this case, we basically we partner with the National High Magnetic Field Laboratory, so in Florida. So they have very fancy different types of AMR equipment as well as MRI. So we're hoping we can see some good results next month. So stay tuned. Finally, acknowledgement. So for the first project, since at that time I was a student, so I will acknowledge the funding agency support me to finish my PhD at the US DOE, and also my PhD advisor Yunping. He just recently retired this year, and Mia was right now is associate professor at University of Colorado Boulder, and she was my co-advisor as well as my postdoc supervisor. And Pania, she's an associate professor at University of Utah, focused on computational mechanics modeling. And Tom, who also retired from San Diego National Lab, surprisingly I cannot find a headshot from the website. And for the second project right now I'm working on, I have to say I'm truly grateful to have this kind of like all-star team. So this project was funded by USDA for a service P3 Nano program. So we have Robert. Robert is a FPL scientist from USDA. Eric, everybody knows him probably. He's a professor at University of Maine. Colleen, she's amazing. She's the director of PGC. She's basically providing me all different types of the cellulose nanofibril. And Jason, everyone knows Jason, professor at Oregon State University. He's amazing. He knows all the knowledge about internal curing, and truly grateful of having him on the team as well. But most importantly, I want to also thank my students, Priyan. So he's doing a fantastic job on this project. And without him, like we're just the people sitting behind, give him the advice. But without him, we can't make this project working. And I have another student, Su Zhang. He's also doing some work with geopolymer, and we're trying to incorporate nanomaterials as well. So hopefully we can put his headshot in some of the slides in the future. To the end, just some take-home notes. So first of all, we all love concrete, right? So that's why we're here. So I don't want to make the take-home notes too boring. So just make one single bullet points. Is that I say nanomaterials have a great potential in concrete applications. It all depends on what kind of application you're looking for, right? So with right now, compared to 20 years ago, I think nanomaterials were very expensive, but nowadays the prices continues going down. I think we have the potential to incorporate them in more and more applications, even like just the civic infrastructure. But I have more take-home notes for the students and postdocs. So I think research is just it's a lot of things, but just do what really excites you and what inspires you and what you truly love. Because otherwise, if you don't have the interest, you don't love the things you are doing, it's very difficult to continue and get some really good results coming out. Then, well, research is tough, but it always paid back pretty well. So this is how like I believe most of the professors were so enjoying our life in academia. It's not because of it's not because of salary. It's not because of the flexibility. It's just because we love the work we're doing. And finally, the patience is a key in research. So sometimes you may get frustrated about the result coming, which is completely out of your expectation. But this is how it works. I mean, fail the experiment doesn't mean you failed your life. So it might be wrong, but it's still in the experiment, but still making a contribution to the community. So Rom took time to rise. I think that's all. And thank you very much. We're happy to answer any questions.